And let's just sketch out what we had last time. So we have our plot of the equilibrium line on the xt plane. And we said equilibrium was the region we wanted to avoid because, of course, there's no net reaction happening there. We also plotted the isorate lines. So we said we had lines that had this kind of shape. So these are some isorate lines. And, and we have orders of magnitude difference among these lines. I wonder if I could do this well enough. Let's see. These Bezier. Okay. Yeah, that doesn't work too well, but anyway, I guess you know what I mean here, right? Let's do another one. So this is the plane. We said this was what nature has given us, right? Nature has dictated that these are the rates. So if you have your reactor here, if you have your reactor, and if X is the current conversion that you've accomplished in that reactor, let's just talk about a batch reactor for now. So there's a certain conversion that you've accomplished, and so associated with that, there's a certain concentration in that reactor, and then there's a certain current temperature there. So when we read this conversion here, we really think of this as a concentration of our reactant. So given a certain concentration and a certain temperature, then there exists a certain reaction rate. So in a way, these are two independent variables that fixes a point. And then if we look at that point, that tells us the reaction rate there. And looking at these isorate lines, this is the highest rate line, right? Remember, for that exothermic reaction, we said down in the corner here, we had the highest possible rate. Then we had another rate line. The rate wasn't as high there. Then another rate line, and that is still lower than the rate over here. So, so we've got the reaction rate increasing in this way. So your reaction rate does get higher as you look like so. And you can imagine as the temperature is rising, your reaction rate is increasing. So that is something that we expect. And now we want to figure out how to navigate the plane. So the problem that we started talking about was, let's say we put a reactor in here, a CSTR, and then let's say we cooled down that CSTR so that we would get back to a reasonable rate region, and then we would introduce to another CSTR here. So we could have CSTRs in series. So we would have a train of reactors. That was our proposal for achieving higher conversions. And the reason we did that was we said, well, when we come along with our reactor, right, we have an operating line, which is our energy balance. And we can see we can't go beyond the equilibrium point here, right? As we are increasing the volume of this reactor, we are going through different reaction rates. Well, you can see I'm going between these two rate lines, but those rate lines are not parallel to this line. And it's not just because my drawing is wonky. It's these lines are generally not straight lines. And especially when you get around here, as you cross these isorate lines, you can see you are going through different reaction rates. And as we increase the volume of the CSTR, we are getting to higher conversions, right? We know that's what happens. If you make your CSTR bigger, then your time in the reactor is increasing. So our conversion is going up as we consider, as we move up along this line here. We know that the gradient of this line is fixed, right? dx dt, last time we said, is minus some theta I over minus some theta I CPI over delta HR. So the gradient of the line is fixed because in the original problem, we said we have pure A, so only component A is coming in here. So that's A coming in, and so our gradient is fixed there. So now we've hit the point where we can't seem to get a higher conversion. And we don't want a low conversion, because if you think about what that will do, if you have a low conversion, then that means we are going to have a high concentration of A coming out here. Well, there are different issues, right? One is you will have a high concentration of A coming out. The other is, well, you'll at least have a high reaction rate there. So there are pluses and minuses to all these design choices, right? So if you do have a very low conversion, then you'll have a high rate, but that means you then have to separate A from B. So your separation costs will go up. You'll likely need a big distillation column over here. Well, I don't want to spend the whole time drawing a distillation column, so I'm just going to let it be wonky like this, right? So you'll have a distillation column, and you'll need to spend a lot more on distillation then. So that's not good. That means your process cost will go up. So your distillation, your separation costs, let's just call it a separation cost. Your separation costs are going up as you allow lower conversions. So what we want to do is get a good conversion, but our worry is that our rate is going to be quite low. So we would like now to cool back, and so we get back to a high rate region. Well, it's not a higher rate region, but we've at least gotten back to the point where when we react again, right, we are still, of course, going parallel to the original line. I guess that's about parallel. But we are getting to a higher conversion. So moving along just this one line is not going to get us to a higher conversion. You are constrained. There is a maximum conversion that you can achieve if you work with just one CSTR. But if you add a cooler, then you can pull yourself back here, right? You drop your temperature of your fluid. So your temperature here is going to be much lower than your temperature here. So you've cooled back to this temperature. You've cooled back perhaps to the initial temperature, right? So this was an exothermic reaction. You came in at T in here. T out was greater than T in. So this temperature was higher. But now we've cooled it back down to T in here. So we've cooled back down here. So we've cooled down to T in. And now the same gradient applies, right? So if you go back to the energy balance, we are going to write an energy balance on this reactor, or rather an energy balance on this reactor also applies. And if you do the development, you'll see it will have the same gradient as the first one. And so now we have a higher maximum conversion available to us. And so we can adjust the volume of this reactor, and then we can choose where to stop here. And then again, we can apply more cooling. So we can apply another cooler here, get back to a T in, and then again, we can apply a reactor, and now we've got a higher conversion available. So that's all fine. Any questions on that so far? So that's fine. That's in principle what we can do. But a question that should occur to us is, well, where must we stop, right? Why did I draw this point here, right? This line is well defined. That's my equilibrium line. The red line, that's a well-defined equilibrium line. But it's a complete free play deciding where to stop here. Of course, I don't want to stop right on equilibrium, right? On equilibrium, that is a higher conversion, but on equilibrium, the rate is zero, right? The equilibrium line, the definition of it is the net rate is zero. The reverse and forward rates balance, so the net rate is zero. And for me to operate on a net rate of zero, I will need an infinite size CSTR. So I don't want to try and build an infinite CSTR in the real world. I want to choose some rate that's not zero. And there does exist a maximum rate in this space. So the maximum rate is where we can imagine the rate changing as we move along this line. So remember, as we choose different volumes, we are moving along this line. And we did draw last time that we could plot the rate, right? So we plotted the reaction rate RA as a function of the volume of the reactor. And we got something that looked like that, right? So there does exist a maximum rate. In other words, there does exist a volume where the CSTR is operating at the maximum rate. And so let's look at this plane and try and figure out where that is. So let's kind of refresh this drawing. Today is the 9th month. Okay, so I'm just going to redraw it now. So here are the axes again. Oops. So there's X and T, and here's the equilibrium line. And here are some isorate lines. Okay, I just want to do one more here. Okay, now let's draw our energy balance line. So let's take a line like, I just want to cross some lines a bit. So let's say our line looked like this, okay? So this is our operating line. And now let's think about, as we move along this operating line, where the maximum rate is going to be. And in fact, one of the things we could do is make a copy of this and say, well, if the line was here, this would be the maximum point. So if you just think about this, remember this line has a lower rate than this line. So the dark blue is the high rate line. So if you move to the left of this point, right? So let's just mark this point. So we have a point of, sorry, this is quite tedious. So we have this line, and I actually want to copy this line now. Okay, so let's think about, as we move along this line, you can see that we are, for all points to the left of this point, we are moving closer to this blue line. So we are going to lower rates down here. All the points along this region are lower rates than the rates on this line, right? Once more, the dark blue line, that's where we have nice high rates compared with this line, right? The paler blue line is a lower ISO rate than the dark blue line. So all points below this one gives us a lower rate region, and all points above this give us a lower rate region also. So going past this point, this is again going closer to the blue line. So that's these are lower rate points, right? So this is the maximum. All points to the left of this point are lower. All points to the right of this point are lower. So this is the point where we get the maximum rate. So we can mark a point here to say that's the maximum rate line, or the maximum rate point. And the same applies here. If you position your operating line here, so if you had used another inlet temperature of that value, then you can see all points to the left of this point are closer to the green line, and the green line is a lower rate region than this blue line. So all points to the left here are have a lower reaction rate. All points to the right here also have a lower reaction rate. So at this point, we have the maximum reaction rate. And then the same applies here. All points to the left of this point are closer to the orange line. And so that's a lower rate region. All points to the right, also a lower rate region. So this is the maximum rate point. And you can repeat this for as many ISO rate lines as you want to show. So we have then marked specific points. We said here was one high rate point, here was another high rate point, here was yet another high rate point, here was another one. And so what we can do then is say, well, all these lines, what's a nice, all these lines are following this kind of shape. So all these lines seem to fit through there. So this gray line is my my high rate line. And so we can label it as such. We can say all these are my high rate, so maximum rate locus of points. So moving along this red line, remember the red line is our original, this dark red line, this line is our original operating line. So moving in this direction along this this dark red line, if my gradient is like this, then my maximum achievable rate is where this red line intersects with this gray line. So if I start at, let's say I start here, then if I wanted to achieve the highest reaction rate in my reactor, I should stop at this point. So in other words, if I am constructing a CSTR, then I need to make the CSTR have a volume that's going to get me only to this point. If I make the CSTR any smaller, then I will be operating at some point below that. So if I'm operating down here, then my CSTR will be at a lower rate. If I operate at any greater value, then my rate will also be lower. So this is the ideal volume for my CSTR. So I definitely want to stop there. And then, of course, we want to cool back down. So we say, well, if that's the best possible point, and find there are other points available up here. So if I look up here, I could have gone further, but we know it's suboptimal. But then that means if I want to be optimal, then my conversion is low. So if I want to get to higher conversions, then I do need to cool everything down. And so I cool down, and maybe I cool down to my initial or my inlet temperature there. And then I use another CSTR. And then again, I'll want to make that CSTR operate at the highest possible rate there. And then again, I can cool down to here. And so I can keep doing this until I achieve my design spec. So maybe my design spec says, well, for this reaction system, we will accept a conversion of this value. So let's say our design spec was that we need to accomplish a 40% conversion in the reactor. That will give us a reasonable amount of separation. In other words, the conversion is high enough that my distillation costs are not prohibitive. So if that was our design spec 0.4, then this is the process we can apply. We can take the gradient, remember sum theta I CPI over delta HR minus. So that's the gradient. And then we move along the line until we reach the maximum rate line. So actually, I should say we first get the gradient, and then we use the gradient on each of our isorate lines to find these maximum rate points. Then we use the maximum rate points to draw the maximum rate line. And then we can take our line, we can take our inlet temperature and use the gradient and step up to the maximum rate line. And then we cool down to the initial temperature, and we keep repeating that process until we satisfy the design specification of 40% there. So that's what we can do to get optimally sized CSTRs and still accomplish the design spec. So we need coolers. So we need those heat exchangers in between, and we are going to need a train of 3 such reactors to get to 40% in this case. Any questions or comments there? So that tells us we need 2 heat exchangers and 3 reactors. And we can have optimally sized CSTRs, and we can reach 40%. Okay, so that's what we would do in the case of the CSTR. And I just want to save this, and let's think about the PFR now. So now let's say this wasn't a set of CSTRs. Let's say this was a set of PFRs instead. So if it's PFR, then the same criterion might not apply, right? Remember, the feature of the CSTR was that you were stuck to one low rate in the whole reactor, right? Let's just stop there, right? So now we want a PFR, and in a PFR, would you want to stop at this point? So let's say this was our inlet temperature, and we are moving parallel to that. Our gradient is fixed, right? Some theta I CPI over minus delta HR. So that's our PFR line. Okay, I'll just put it here. So if your maximum rate path is here, right? We know this is the point where we have the maximum reaction rate. This is our maximum reaction rate. If this is our starting temperature, and if that's the gradient of our line, this is the highest reaction rate we will accomplish. Then would you stop at this point, right? For the CSTR, we stopped on this point. For the PFR, would you stop here? Any takers on that? So if you think about it, you've just reached a good rate here. And if you stop there, then that means your exit rate, the reaction rate that you have here is this highest rate. Now, why would you do that? Why would you stop just when it was getting good, right? When your rate was getting good, what you really want is for the highest rate to be the average rate across your whole reactor. So if you were plotting the rates, right, maybe the rate was doing something like this. So fine, you will have lower rate regions, but that's fine. Why would you stop at the maximum rate? So I should have run it differently. So if your rate was going up and then you reach the maximum rate, there's no reason to go and stop the system reacting and going. There's no reason to say that's where I want to stop, because that means my average reaction rate will be some value here. Whereas if we extended this reactor and let's say to this point, then that means your average reaction rate would be that value. The reason we didn't do it in the case of the CSTR was because in the CSTR case, everything is stuck to one rate. So if you choose to stop on this point, then that means at every point in that reactor, you will have that high reaction rate. Whereas in the PFR case, we know that all these values apply. You will be able to find a point in your PFR which has that reaction rate, which has that reaction rate, and so on. So there's no reason for us to stop on this, on the maximum rate point. You would rather keep going and say, well, the rates here are not as high as the rate here, but still, I would like to have on average the maximum reaction rate. Of course, we can't keep going forever. There is equilibrium. And so as we get closer to this point, for a small improvement in conversion, we will need massive volumes. So we might need hundreds of cubic meters just to get a 0.001 increase in conversion. So as you get close to equilibrium, that's what starts happening. So we do still have to stop at some point, but the point of optimal stopping, the optimal reactor volume, that's what we mean. The optimal reactor volume in the case of the PFR is different, right? In the case of the CSTR, it's very, very clear you stop here. In the case of the PFR, we just want to go to as high a rate as possible where the reaction rate is still reasonably good. And so there is a kind of rule of thumb that is available in reaction engineering, which is we just stop 10 degrees short of the equilibrium temperature. So remember earlier, the way we found the maximum rate line, we took the original line and we drew a bunch of parallels to it. So we took that line and we shifted it. Well, what we can do now is take that line and look up the equilibrium values for that line. Okay. So as you move this line around, you can look up the equilibrium value. So this is where the line intersects with equilibrium here. If you move it here, that's the equilibrium value. When you move it here, that's the new equilibrium value. So in other words, we can look up for equilibrium along this line, the point to avoid, right? Equilibrium is the point to avoid. And so the rule of thumb that's proposed, which gives fairly good results, is that we would stay just 10 Kelvin short of the equilibrium temperature. So along this line, this is the equilibrium point. So you just project that down and you look at the temperature there. And then you say, well, I don't want to go all the way to equilibrium temperature. I want to go to 10 degrees short of the equilibrium temperature. And that's all you do. So you look up the equilibrium temperature and you just shift 10 degrees to the left of that. So for example, if this was your equilibrium temperature, that's your equilibrium temperature, then you just subtract 10 Kelvin from that, and then you say, that's the temperature I want to stop at. And of course, this is all happening with respect to our operating line. So let's put in the operating line again. So you would say, for this operating line, 10 degrees short is here. So this is another point I can propose. So I want to stop here. And so you do that for several choices of inlet temperature, and that will give you another line here. So we've got a third line, right? The first two lines, the equilibrium line, then the second line was the maximum rate line, and now there's the 10 degrees shy of equilibrium line. So that's a new line. Now let's see if we can do this. So this is the optimal stopping point for the PFR. You would say for this PFR, then what I want to do is stop at this point. So my PFR must only be this big. For my CSTR, it needs to be this big, because if I go beyond this point, then my whole CSTR will have a low rate. For my PFR, I say I'll stop here because this lets me stay in the high rate region for as long as possible, or stay near the high rate region as long as possible. Okay, and so that's how we design the PFR. And in the case of the PFR, we will also need to cool things back down for us to reach the higher conversion region. So we cool things down, and then we add another PFR here, and so on. By the way, I draw my cooler, my heat exchanger, deliberately this way. So when I want to show that it's a cooler, I draw the arrow pointing up to signify the temperature is going up on the fluid in the heat exchanger. So remember, if we are trying to cool down this line, then our heat exchanger line will heat up. So that's a cooling heat exchanger to me. Okay, so for the PFR, we can go further than the CSTR, but we need to stop at the 10 degrees to equilibrium line, and then we can cool back down to the original temperature. So for example, stop there, and then we go up. We will be parallel to the original line. We have to stop on 10 degrees to equilibrium, then we can cool down and keep going until we meet the requirement, the 40% or whatever it is. Okay, any questions or comments on that? Okay, now we have been saying we want to stop on this point, as if we can stand there and say, okay, stop reacting, right? The way that we get this to stop reacting is to make the reactor the right size. So in the case of the CSTR, we know we have minus, or rather, FA naught X times or equals RAV. So when we design these reactors, what we have to do is look up. So for the CSTR, we look up this value. So what's nice is on these plots, we can just read off the reaction rate there. So we read off this as a number, and then we also have the conversion. So if you look at this point, that is pointing at a certain conversion. So you can read off the conversion there. We have also specified the molar flow rate. So if you look in that problem, we have specified a molar flow rate. So RA is known, X is known, FA naught is known. So the only thing not known is V. In other words, we can solve for the required volume to get us to this conversion at this temperature. Okay, so that's one. That's what we do in the case of the CSTR. CSTR is very easy. We just look up the rate and the conversion, and that's it. In the case of the PFR, we then have to think about all these points. So looking along this PFR, let's draw it here. So we have a series of points, and all these points exist. In other words, we can find a point in the in the PFR where the conversion is this value, and the rate is this value, and the temperature is this value. So it's going through all these points, right? In the case of the CSTR, it's not going through all these points. If you, I need to point here. For the CSTR, the whole reactor is sitting here. You won't find a point in the CSTR here. So there's no conversion and temperature of these values in the CSTR. The whole CSTR is sitting here. Whereas for the PFR, it's continuous. You are seeing all these values here. So in the case of the PFR, this is what applies. It's FA naught times dx dv equals RA. And I just want to write the CSTR here. So maybe let's just to get them sort of in the same form. Let's put that like that. Okay, so that's the CSTR, and this is the PFR. And so that's the standard design equation for the PFR. It's not in a nice suitable form for us to get a volume. So what we have to do is just integrate this equation a bit. So we can say here, dPFR equals dx over RA. And I'm just going to take this across on the other side. Right, so just check you agree that from the original design equation, this is what you get if you just do a bit of calculus there. So if you just integrate both sides by dPFR, and then you get this form, right? And so the volume of the PFR that we need is going to be the integral over all this. So that's equal to the integral dPFR. So that's equal to the integral of this. And of course, RA is a function of X here. So we need to do this integration for us to estimate the required volume for this PFR. And we can say that's the required volume to stop at this point. So that's how we determine the volume for us to reach a specific end conversion. So here the conversion, it's between the limits that we found. So it goes from 0 to and we specify an end conversion. So to do this calculation, you can write this as approximately equal to, you can say that's approximately equal to, and we'll just write this as the sum, and we can write this as a delta x. So delta xi, right? So just check that you agree this integral is approximated in a Riemann way by this thing, right? You can see it's the same. This is just the discrete form of this. So to work out the volume of the PFR, we pick a series of points along this line. So we take this and we pick a series of values. Let's do it separately. So let's say we look at that line, and then we can see a couple of x values. So let's write them in. So let's say this was the x value of 0.2. Let's actually draw some points. So there's let's say we've chosen these subdivisions along the line. So this will be in x. We can say here x equals 0.2, 0.28, maybe 0.34 and 0.4. So let's say we had chosen those points, and then we would also specify some rate values. So looking along that line, we would say this reaction rate is maybe 0.03, and the rate would go up here. So it would be maybe 0.45. Maybe it's coming back down again. So maybe 0.42 there. And then it will definitely have gone down by here. So 0. Maybe even 0.15, something like that. So now we have a series of points along our line. So once more, to get these values, you will just take the line of interest. So you'll say for the PFR, I'm stopping here. For the PFR, you'll say, this is where I'm going to stop. And I've started with this temperature. So this is the line of interest to me. And then you'll pick points along this line. Obviously, the more points you pick, the more accurate it will be. But for this course, of course, we just take a reasonable number of points. And then, just pick points where you can easily read the rate. Like if you can see this rate line crosses over here, then it will make it easier for you to just read off the value of the rate to fill in down here. Right? Conversion is very easy. You can just read off conversions from this axis. So then look for example, over here, there's another intersection there. So look for convenient points where you can read off rates quite easily. Okay, so let's just copy that across so we can do the calculation. So those are chosen points. Oops. And so we would say the volume of the reactor for the PFR. So the PFR is approximately equal to, and then delta X, the first delta X here, well, let's write it in full. So the first delta X is going to be 0.28 minus 0.2 divided by, and then the reaction rate, and it should be the mean reaction rate in this region. So this should be 0.3, by the way, not 0.03. Well, or it could be 0.04 instead. But anyway, let's just take it as 0.03. So we would normally, we should take the average between those 2 points. So I'm going to say here the average in this region is about 0.22. 0.22. Okay, so that's one. And then the next one is 0.34. So this is 0.34 minus 0.28 and divided by, and let's write out the averaging here more carefully. So it's a half times 0.45 plus 0.42 plus, and the last one, 0.4 minus 0.34 divided by a half, and it's 0.15 plus 0.15 plus 0.42. And that's pretty much it. So you just do this calculation and that will give you the volume of the reactor. We should check the units. There is an FA naught. We have to multiply all this by. Why did I write B here? So remember over here, this has units of conversion, so that so no units there. Down here, you've got units of reaction rate. So this is moles per second per cubic meter. And then you are multiplying by moles per second. So all of this works out to cubic meters, right? So that's how you choose some points, and you can approximate the area along the line there. And that is how you estimate the volume of that PFR. Okay, any questions or comments there? So practice this. Be sure you can do these integrations quickly. Don't take too many points, right? Even if you take 3 points, it's fine. And just get a reasonable approximation to the volume. And that's it for today.